Welcome to Chapter 7, where we're going to be learning about the Neoclassical growth model. This is going to be part one of a two-part lecture on this chapter, and then there's going to be a few additional videos to help us work through some of the mathematics that are used to actually solve this model out. So let's just get started, I guess. So last time we did a little dynamic optimization. We learned about what the Euler equation was and how to graph out the agent's preferences. And we learned this over a two-period model. So the idea was like after period t plus 1, the world just ends, which isn't a bad assumption to make. But if you want to learn a little bit more, right, you want to be able to use this dynamic macro in kind of like a more believable context, I guess. Maybe you want to extend that beyond two periods. So we're extending that two-period model out to an infinite horizon model. And we're also going to be endogenizing output, which changes our constraint just a little bit. And when we do that, well, that actually gives us our neoclassical growth model. And the nice thing is, instead of using a nice little learning tool with the two-period model, we're actually doing like a real economic model that was used for quite some time. It's really like the workhorse, like dynamic general equilibrium model in macroeconomics. So now we're going to start learning about macro the way macro guys do macro, which is pretty cool, I think. So let's go ahead and get moving on here. What are we going to do? Well, first we're going to cover household preferences. We're going to learn about the utility function, and it's really just a restatement of what you saw in Chapter 5. So we'll go through it kind of quickly. Next, we're going to cover the household's constraint, which is just a restatement of what we saw in Chapter 4. Okay, well, it's not that bad. We're going to spend a lot of time on the optimization methods to find a solution to the problem, which is where we're going to be using what's known as dynamic programming and the Bellman equation. We're going to get our general equilibrium, and with the general equilibrium, it's just listing out like all the relevant equations to close the model out, and that's where we can allow for shocks to enter. Then we're going to have our steady states. We're going to solve for the steady states. Not too different from Solo, but it's now going to include household preferences. So we'll see when we do the steady state stuff how it differs from Solo. And then we're going to talk about some shocks to the model, namely how the model responds to technology shocks. So preferences. Let's start with preferences. We have a utility function. We're going to assume there's one household in the model, and it's a representative agent, meaning that this person is representative of like the whole economy. And the household's utility function is just what you saw in the previous chapters, except this time it's not two periods, it's an infinite horizon. It's an infinitely lived household. In the two-period model, right, the household lives for 2 periods and then the world ends. And in that terminal period, they don't do any more investment. Investment is equal to 0 because why would you save for when there's not going to be any existence in the next period? It's kind of dumb, right? In the infinite horizon model, that investment carries over period after period after period. Now, it's economically convenient because, think of it as like an uncertainty. You don't really know when the world's going to end. You could also think of it as like a dynastic planning approach where you're the head of the household, and then when you die, your child becomes the head of the household, and then they die and their child, and so on and so forth. And there's this constant planning going on. It's also very mathematically convenient, which is very nice for us. And the household is going to choose to consume or save over this infinite horizon, and then it gives us an optimal consumption path over said infinite horizon. Cool, works for us. Now, the utility function represents an agent that is infinitely lived, and we would have the sum as t goes from 0 to infinity of beta to the t times u of ct. Now, in this class, we're dealing exclusively with log utility, so it's the natural log of consumption. So it's the sum as t goes from 0 to infinity of beta to the t times the natural log of ct. So for our marginal utilities, the nice thing, right, the derivative of u with respect to ct is always going to be 1 over ct. The derivative of u with respect to ct plus 1 is always going to be beta times 1 over ct plus 1. And these marginal utilities will actually hold for every model in the course, save like maybe one or two things. There's one model where we've got money and I think labor or leisure in there, but it's all additively separable. So marginal utility of consumption is always going to be what you see in equation 3 and equation 4. So ultimately, the only thing that's really going to change is the constraint, which is what we get to next. What's the constraint? Well, the economy's got a resource constraint, and it says expenditures can't exceed income, just like what we saw in Solo, y equals c plus I. Output is split between consumption and investment. Cool. Output's given by the Cobb-Douglas specification, y equals a times k to the alpha. We've seen that. And investment evolves according to the law of motion of capital, which is I equals kt plus 1 minus delta times kt. Now, in case you're like, okay, well, what's the next thing that we do? Just match everything up with the respective colors. So what's pink in equation 6 gets substituted in for what's pink in equation 5. What's blue in equation 7 gets subbed in for what's blue in equation 5. And that gives me equation 8. So I take those three constraints and I combine them into one, just like we did with the Solo model. And then, for reasons that we'll be seeing pretty soon, I'm going to take equation 8 and I'm going to solve it for c sub t. And now, with equation 9, where c is equal to output minus investment, I'm now ready to do the optimization stuff. And the idea is I'm going to take the derivative of that utility function with respect to c, subject to the constraint, set it equal to 0, and find the optimal consumption path over time. Mostly. So now we've got a general idea of what we want to do. So let's recap what we've got. We've got this utility function. I want to maximize my consumption over an infinite horizon of beta to the t times the natural log of consumption. And I'm doing so subject to the constraint ct equals at times kt to the alpha minus kt plus 1 plus 1 minus delta times kt, or ct equals output yt minus investment it. Now, there's a couple different ways that we can solve this out. We can do like the calculus of variations. It'd be like Lagrange multiplier stuff. Or we can solve this out via like recursion, what's known as dynamic programming. I am partial to dynamic programming. What it does is it's going to take this infinite horizon model and it's going to turn it into a two-period problem. And it does so recursively. So it's very easy, very simple to solve out. And you also don't have to substitute out a bunch of Lagrange multipliers, and you don't have to worry about any of that crap. It's much more straightforward than that. The only thing is you have to take a couple of derivatives for each choice variable. You got to take two. But beyond that, it's really not that bad. And if this isn't quite your forte, if you're not really feeling it this way, there's a two-period model that you can solve out. You've already seen the two-period model, so you can kind of just do it that way. And there's a video that I'm posting that's going to explain that as well. So, yes, there we go. What are we going to do? Well, we're going to take equation 10. All right, so that is this utility function. I want to take this, and because this is an infinite series, right? If you've had calculus 2 and you've learned about infinite series, this is an infinite series. It's an infinite geometric series, and it's geometric because of that beta term. That beta is 1 over 1 plus rho to the power of t. So that guarantees we've got a convergent geometric series. So we can play around with it a little bit, and it makes things very nice. So I'm going to take that, and I'm going to pull out that first natural log of ct, and I'm going to re-index that sum. So it's a natural log of ct plus t goes from 0 to infinity of beta times t plus 1, or beta to the t plus 1, sorry, times a natural log of ct plus 1. I can pull that beta out, right, because it's beta to the t plus 1. So it's beta to the t times beta. So I can just pull that beta out and put it in front of the sum. Because remember, the order of multiplication doesn't really matter. So now it's a natural log of consumption plus beta times the sum as t goes from 0 to infinity of beta to the t times a natural log of ct plus 1. Well, we know this is a convergent geometric series. So we can kind of think of it as like I got today's stuff and then I got tomorrow's stuff, and tomorrow's stuff converges to something. So I know what it converges to. That makes it really easy. So here's what I'm going to do. I'm going to rename this whole equation. It's going to be v now instead of u. And that second part I'm going to name, so this u gets renamed to v of ct. This part here, so everything from the sum outward, gets renamed to v of ct plus 1, because I know it converges to something. because it's a convergent infinite geometric series, right? That part's already been well established. So what it's doing is it's taking that time from tomorrow to the infinite horizon, and it's just going, well, just think of it as like one period. If you remember that musical Annie, she's singing that song, Tomorrow's Always a Day Away. Think of it that way, right? Tomorrow's always going to be a day away. So we've got today and tomorrow, but then tomorrow rolls around. Tomorrow now becomes today. What do we have? We've got today and tomorrow. Cool. Well, the day after tomorrow rolls around. Well, the day after tomorrow becomes today. We got today and tomorrow. It's always today and tomorrow, today and tomorrow, today and tomorrow, today and tomorrow. So because of that, it just kind of boils it down to a two-period problem, and it does so recursively. So I've got v of ct equals the natural log of ct plus beta times v of ct plus 1. Cool. Now, if you're like, okay, am I going to have to do this stuff? No, you're not. I'm showing you how to get to what you're going to need to use just so you know where it comes from. So you're not like, well, I'm just doing this and I don't know why I'm doing it. So equation 12 is going to be really important. We're going to make like 2 changes to equation 12. And then from then on out, it's really going to be about what you see for the rest of the course. So what are we going to do? Well, I'm going to plug that constraint in for CT in equation 12. So I got the natural log of CT. I'm going to take CT equals output minus investment, this stuff right here, and I'm going to plug that in right here. What does that do? Well, I just natural log of this stuff, which was CT, now it's output minus investment, because this is equal to CT, plus beta times V of KT plus 1. Now, why am I doing it? What happened to that V of CT? Well, I substituted consumption out, right? It's now in terms of capital. So, because it's in terms of capital, this V of CT becomes V of KT. And then I've got plus beta times V of KT plus 1. Now, one thing I want to make painfully clear, when you're doing dynamic programming, when you're doing this type of like an optimization method, you substitute everything in for CT here. Leave this CT plus 1 alone. Don't substitute anything in here. It's just the natural log of CT where the stuff gets substituted in. V of CT plus 1, or once we plug everything in for CT here, becomes V of KT plus 1. Don't plug anything in here. Just keep this as it is. Keep this nice abstract function, V of KT plus 1. What do I want to do now? Well, now I want to choose KT plus 1 instead of CT. Why am I going to choose KT plus 1 instead of choosing CT? Why am I choosing tomorrow's capital instead of today's consumption? Well, here's the cool thing. If we do that, what I'm doing is I'm technically choosing consumption by default if I choose capital. So if I choose capital, let's think about this, right? You choose KT plus 1 because you can't choose KT. That was already chosen yesterday, right? You can only choose KT plus 1. So if you choose KT plus 1, well, you choose YT plus 1 because output, tomorrow's output, is a function of tomorrow's capital stock. Tomorrow's capital stock was chosen today. So assuming we have K naught given, and that's just like an initial condition that we need. Assuming K naught's given, well, that means KT is given. K naught's like the capital stock at the beginning of time. KT is the capital stock today, which was chosen yesterday. KT was chosen yesterday, so YT has already been chosen. You can't affect KT. If you can't affect KT, you can't affect YT. So YT's already been chosen, right? YT we already know. So if we choose KT, or KT plus 1, we choose KT plus 1 with YT already chosen. Well, we're picking IT because remember KT was already chosen. So if you look at the investment stuff, this was already this is chosen. This is chosen. This is the only guy I can affect. But when I affect this, I affect tomorrow's output, and I also decide how I want to consume today, so I can back everything out. So YT was chosen yesterday, but by choosing KT plus 1 today, I choose investment today. So with YT output and investment chosen, I can back out what consumption is. Cool. So I have in equation 14 what's known as a Bellman equation. It's also a value function, and it's recursively expressed as this. So I got the max, I want to maximize KT plus 1 of V of KT, which is equal to the natural log of output minus investment, or consumption, plus beta times V of KT plus 1. So the natural log of output minus investment, or the natural log of consumption, is today's utility. That beta times V of KT plus 1 is everything else. And I want to choose KT plus 1 instead of CT because, like I said, if we choose KT plus 1, that implies an optimal choice of capital, which then gives me an optimal investment choice, which gives me an optimal consumption choice. So let's spend a little bit more time on this KT plus 1 thing, because I really want to make sure that this makes sense before we move on. So we're choosing KT plus 1 because for investment, remember, I is equal to KT plus 1 minus 1 minus delta times KT. KT plus 1 is our choice variable. So if we choose KT plus 1, we choose investment. And if we choose KT plus 1, we choose YT plus 1. And if output's already been chosen today, it was chosen yesterday, and I choose KT plus 1, I'm choosing investment, which then lets me back out consumption. I pick output tomorrow, investment tomorrow, and thus consumption tomorrow. That's kind of cool, isn't it? So by making that one choice, we get to decide for all these other things. That's the nice thing about dynamic programming. So with this Bellman equation, what I want to do is I want to take the derivative of V of KT with respect to KT plus 1. Why is it with respect to KT plus 1? Because KT's already been chosen, right? I need to know what KT plus 1 is going to be. So I take the derivative of equation 16 with respect to KT plus 1, and then I set it equal to 0. Now recall, consumption is equal to output minus investment. So the pink stuff minus the blue stuff is equal to consumption. So the natural log of that pink stuff minus the blue stuff is the same as the natural log of CT. So really what I'm doing is I'm taking the derivative of U of CT with respect to CT, kind of, think like chain rule, and, well, just then making one little tweak to, be consistent with the chain rule. All right. So we got equation 17, which is the same as equation 16, which is the same as equation 14. Right? It's just now equation 17 because it's on slide 16 instead of slide 14 or 13. So I formulate my Bellman equation in terms of K instead of C. And I want to take the derivative of V of KT with respect to KT plus 1 and set it equal to 0. Right? So what am I going to do? Well, CT is a function of KT plus 1, right? So if I've got the natural log of CT and CT is a function of KT plus 1, think of it as like the function of CT, like f of g of x, right? Or really, I guess, f of g of xy. And I want the derivative of that with respect to x. What do I have to do? Well, I got to take the derivative of f, and then I got to multiply the derivative of f by the derivative of g with respect to x. So think of it as like peeling an onion, right? If you're a little confused, stick with me. I promise you we're going to get to a point that makes sense. All right, so think of it this way, right? You got y is the natural log of x. What's the derivative of that? Well, it's 1 over x. All right, suppose x is a function g of another variable z, right? And I want dy dz, the derivative of y with respect to z. Well, I'd have dy dx, 1 over x, right, times dx dz, x prime of z. That's what we're going to be doing with this constraint. So if you've got a function like v of kt is like u of ct of kt plus 1, well, I need to get the derivative of v of kt with respect to kt plus 1, I need the derivative of my utility of consumption with respect to consumption times the derivative of that constraint, which is consumption as a function of other stuff, with respect to kt plus 1. So if I want the derivative of my Bellman equation with respect to kt plus 1, we're going to do this piecemeal. So I'm going to start with that first term, the natural log of at times kt to the alpha minus kt plus 1 minus delta times kt. And we're going to deal with that beta times v of kt plus 1 stuff a little bit later. So what's the derivative of the natural log of at times kt to the alpha minus kt plus 1 minus delta kt with respect to kt plus 1? Well, take the derivative of the outside first, multiply it by the derivative of the inside because of, well, the chain rule. Okay, so I get my derivative of v of kt with respect to kt plus 1 is 1 over output minus investment, right? At times kt to the alpha minus kt plus 1 minus delta kt. And I'm going to multiply that by the derivative of that constraint with respect to kt plus 1. And then I got that beta times partial v of kt plus 1 with respect to kt plus 1 equals 0. Let's look at just this stuff first. I want to look at just this. So I need the derivative of that inside part with respect to kt plus 1. Well, what is that? Let's go through this piece by piece and see what we're looking at. Well, I want kt plus 1, right? At is not kt plus 1, it's at. Kt is not kt plus 1, that's kt. Again, kt is not kt plus 1, it's kt. The only kt plus 1 I have is right here. And its leading coefficient is 1, well, negative 1, and its exponent is 1, right? So the derivative of what's in the parentheses here with respect to kt plus 1 is just negative 1. So really, the derivative of that Bellman equation is 1 over pink stuff minus the blue stuff times negative 1 plus beta times this thing. And we'll get to this thing later. Now I can simplify this guy a little bit. Negative 1 over all this stuff. But this stuff is equal to CT, right? So I can substitute that back in there, and I get negative 1 over CT plus beta times V of KT plus 1 with respect to, or beta times the partial of V of KT plus 1 with respect to KT plus 1, and this whole thing's equal to 0. Right, we're almost in business. Almost, not quite. We just got to do something about what's in this like pretty little teal color here. Right, it's partial of V of KT plus 1 with respect to KT plus 1. Now this sucks because those time subscripts don't align. So I can't just go, hey, I'm going to take that partial, that dVkt, dkt plus 1 and like play with the time subscripts there because they don't match up. They'll never match up. So I got to do something else. What I can do is I can take the derivative of V of kt. So I can go back to my original Bellman equation. And I can take the derivative of that with respect to kt. And then update the time subscripts by 1 period. Nothing about that's cheating, so this works. So we go back to our original Bellman equation. V of kt equals the natural log of pink stuff minus the blue stuff, right, consumption, plus beta times V of kt plus 1. And from this, I take the derivative with respect to kt, which gives me this. I get 1 over that stuff, right, 1 over ct, times the derivative of the inside, that constraint thing, but now it's with respect to kt and not kt plus 1. So I'm going to simplify this a little bit more. It's 1 over ct times the derivative of that constraint with respect to kt. Now the derivative with respect to kt of that inside stuff, this stuff right here, right, this is a kt, so we're doing something with this function here and getting its derivative. And this is a kt, so we're doing something with this here and getting a derivative. But this kt plus 1 is not kt, it's kt plus 1. Time subscript's not the same, so this differentiates down to 0. So what am I going to do? Well, I take the derivative of this with respect to kt, and it's alpha times at times kt to the alpha minus 1 plus 1 minus delta. Because I take this exponent, bring it down, multiply it by the leading coefficient, subtract 1 from the exponent. So that gives me alpha times at times kt to the alpha minus 1. And then I got this kt to the first power, so the derivative of 1 minus delta kt is just 1 minus delta. So I take that. Cool. So that gives me my partial of v of kt with respect to kt. So I'm really just one step away from my partial of v of kt plus 1 with respect to kt plus 1. Right? Because equation 19 is partial of v of kt with respect to kt. But if we go back a little bit, I need partial v of kt plus 1 with respect to kt plus 1. This is my partial of, where are we? V of kt with respect to kt. Right? Equation 19. But if I just add 1 to every t subscript I see, I update it 1 period essentially. Boom. That gives me equation 20, which is what we had in our first order condition right here. Sweet. So if what I've got here, I'm circling my mouse around, what I've got here is equal to what I've got here, this guy is equal to this guy, which is then equal to this guy, then I can take 1 over ct plus 1 times alpha times at plus 1 times kt plus 1 to the alpha minus 1 plus 1 minus delta and plug that in to that first order condition that I got. So before I do that, before I plug that stuff in, get a nice little result here, let's look at what equation 20 is. What was it telling me? Well, that inside derivative thing is alpha times at plus 1 times kt plus 1 to the alpha minus 1 plus 1 minus delta. Okay, let's start with that alpha times at plus 1 times kt plus 1 to the alpha minus 1. That's my marginal product of capital. It's the amount by which an additional unit of capital increases production, thus income. So it tells me how much extra income I'll get tomorrow if I invest 1 more unit of capital today. So if I invest 1 more unit of capital, that marginal product of capital would be equal to alpha times at plus 1 times kt plus 1 to the alpha minus 1. All right, what's that 1 minus delta stuff? Well, delta is the amount of capital that depreciates. So 1 minus delta is the amount of capital that will not depreciate. And it's accounted for in that derivative because I need to know how much capital carries over each period. Now, at the margin, depreciation is constant, so there's no k attached to it, right? And we're making this decision at the margin. Thus, it's constant depreciation. Doesn't need to be a k attached to it. So this whole derivative just tells me what the marginal product of capital is, controlling for depreciation. It's the marginal benefit of investing 1 additional unit of capital, thus saving more. So let's take that partial of v of kt plus 1 with respect to kt plus 1. And since this is equal to this, I can plug that in for this over here. And that gives me equation 21. All right, but remember the minus 1 over this pink stuff minus the blue stuff, that's just minus 1 over consumption. So, well, that's going to simplify down. But let's just take this guy and add this to both sides. It's negative 1 over this stuff. And we've got 0 over here. So if I take this and add it to both sides, well, now I've got 1 over consumption equals beta times 1 over ct plus 1 times the marginal product of capital less depreciation. So if I sub c sub t back in, well, I get this really nice function. 1 over ct equals beta times 1 over ct plus 1 times the marginal product of capital less depreciation. This is my Euler equation. What is the Euler equation again? Well, the Euler equation tells me in dynamic optimization problems, it is a nonlinear second-order difference or differential equation that characterizes the evolution of a control along any optimal path. It's a necessary, although it's not a sufficient, condition for the household's optimization problem to achieve a maximum. In dynamic macro, the Euler equation tells me the marginal rate of substitution of consumption today for the marginal rate of substitution of consumption tomorrow, weighted by the expected rate of return of capital. So, think of it as like a balancing act, right? Like, well, if you remember the Euler equation from chapter 5, it's the exact same thing. Just what was in the parentheses there was 1 plus the real interest rate. This is actually 1 plus the marginal product of capital minus depreciation. But it's the same thing. And in a future lecture, you will actually see that they are, in fact, the same thing. It's just, well, one is like with endogenized output and the other one isn't. But when we add bonds in and we have a real rate of return on bonds, then you'll actually see the rate of return on bonds, the real interest rate, is equal to the marginal product of capital less depreciation. So if you're like, hey, that looks kind of like what we saw, but not quite, well, yeah, it's kind of not quite, but still the same. I know it's a little confusing. Stick it out for a couple more lectures and you'll see what I'm talking about. So let's review the problem, right? We had this utility function. We wanted to maximize our consumption over an infinite horizon, subject to the constraint that consumption is equal to output minus investment. I formulate my Bellman equation. V of kt equals the natural log of ct plus beta times v of kt plus 1. Now, as I'm going through this, let's recap. This is the stuff you'll actually have to do. So me formulating the Bellman equation, you don't have to do that. All that weird partial stuff like the, what is it, like, with this delta over delta kt of this stuff, like, you're not really going to have to do this. Do what I'm doing in the let's recap stuff, right? So we've got this objective function, this utility function, and this constraint. I have this Bellman equation, which it's almost always going to be this. The only difference is you'll have more arguments in the v function. But you substitute c equals output minus investment in for consumption in equation 26, and that gives you equation 27. V of kt equals the natural log of output minus investment, or pink stuff minus the blue stuff, plus beta times v of kt plus 1. Now, you can just keep ct in there if you want, but you got to be cognizant of the fact that you'll have to differentiate across the constraint that ct is in terms of. Here it's in terms of capital. So you take the derivative of equation 27 with respect to kt plus 1. That derivative is this, minus 1 over alpha, or at times kt to the alpha minus kt plus 1 plus 1 minus delta times kt plus beta times the partial of v of kt plus 1 with respect to kt plus 1. This is a first order condition, right? You're taking the derivative of this value function and you're setting it equal to 0. That's giving you your maximum. But now you just need to solve, well, first we need to figure out what that partial v of kt plus 1 with respect to kt plus 1 is. So what do? Well, I got to take care of that thing. So I go back to my Bellman equation. I go back to equation 27. And instead of taking the derivative of this with respect to kt plus 1, I do it with respect to kt. And when I do that, well, it's the partial of v of kt with respect to kt plus 1, not the partial of v of kt with respect to kt plus 1. So just the partial of v of kt with respect to kt. It's equal to 1 over ct times alpha times a times kt to the alpha minus 1 plus 1 minus delta. Cool. Now, when I'm doing this part, I don't set this equal to 0. Why don't I set this equal to 0? Well, because once we update this by one period, we'll see this is equal to this. And this is not equal to 0. This whole thing is equal to 0. If this were equal to 0, well, you'd have a problem. So when you take that second derivative. Well, it's a first derivative. But you take another first derivative of that Bellman equation. You don't set it equal to 0. All right, it's just the derivative of v of kt with respect to kt plus 1. That's set equal to 0. V of kt with respect to kt, not set equal to 0. All right, but you update this one period. You get the partial of v of kt plus 1 with respect to kt plus 1 equals, move that mouse there so the thing goes away, equals 1 over ct plus 1 times alpha times at plus 1 times kt plus 1 to the alpha minus 1 plus 1 minus delta. And you take that and you plug it in for the partial of v of kt plus 1 with respect to kt plus 1, and that gives us this, where what is in teal was just substituted in, right? I try to keep this stuff color-coded so you can sort of follow what I'm doing because, I don't have a whiteboard that I'm standing in front of, and I'm not getting any real-time feedback, so I'm trying to make sure it's as easy to follow as possible. But, yeah, so we get this right here. I'm going to substitute CT again, so I get minus 1 over CT plus beta times 1 over CT plus 1 times the marginal product of capital less depreciation. Is that equal to 0? Well, I got a minus 1 over CT on one side. I got 0 on the other, so I'm just going to add 1 over CT to both sides. And that gives me my lovely, handy-dandy Euler equation. Now, this looks like a lot of math, I know. But the thing is, it's really just like 2 derivatives and then some algebra. And it's always going to yield something of the form 1 over CT equals beta times 1 over CT plus 1 times stuff. The only difference is what is going to be in that stuff. In this case, it's just that stuff is this stuff right here. But if you have bonds in there, if you've got money in there, well, the Euler equation for capital will still be this right here, but you'll also have an Euler equation for bonds and an Euler equation for money, which you'll see a little bit later. So, don't worry just yet. If you get a problem like this on a homework or on an exam, and the setup is anything even remotely like, let's go back to where we were. Where are we? And it's anything even remotely close to this right here, then you'll probably be in good shape when you recognize this will always be the same for capital. Always. So if you got to get an Euler equation for capital, this is it right here. And, these exams are take-home, kind of by design of the course, right? Because it's, an online course. And while the homework is take-home by design because it's homework. So you can always just review the notes and just kind of, work through what I did in the notes for what you're doing on the homework or the exam. But if you get 1 over CT equals beta times 1 over CT plus 1 times alpha times AT plus 1 times KT plus 1 to the alpha minus 1 plus 1 minus delta, that's your Euler equation for capital. It's always going to be that. So if you see that, and you need an Euler equation for capital, that's it right there. Then just show me how you did it. Problem done. Problem solved. Done. So it's going to take a little bit of practice, I know, but you'll have plenty of opportunities to practice this stuff. There'll be example videos going up, and you'll have a little bit of homework where you can play with this stuff. You'll have plenty of opportunities to learn this. So if you don't get it just yet, don't freak out. If you are freaking out, feel free to email me, message me. I'm happy to walk you through this one-on-one and work with you guys. But this does wrap up the lecture for today. I know there's a lot of math. The next lecture has a lot of math, but it's at least math that you've seen before. It's just like what we did with the solo model for the steady states. So I'm going to end the talk here for now. I spent a little bit more time working on some examples. But we'll play with the constraint a little bit, maybe add another term into the utility function, things like that. And then we're going to move on to the general equilibrium stuff and play with the steady states of the model. And the nice thing is, this is the hardest stuff that we're going to do all semester. Once you get this down, there's no new math that you need to worry about. Everything else is just using these math techniques that you're learning from this presentation right here, from this lecture. So yeah, once you get this, everything else is a cakewalk. Literally everything else is just learning the economics. No more math. So yeah, thank you for watching this. I hope this didn't scare you away. If it did, well, don't leave just yet. I promise you, everything gets easier from here. Promise that. So yeah, thanks for watching. Stay tuned for the next couple videos. They are coming, and I will see you guys in the next lecture.